of yesterday, which I went too fast, so I think it was a bit unclear. So the question is the following. You just take the state psi of two spins, okay, which is alpha up, up, plus beta up, down, plus gamma down, up, plus delta down, down. Okay? So the question was, I want to compute the reduced density matrix tracing out the B, okay? The B spin. So which means that I have to take the full density matrix of this pure state and do the partial trace. So I think for the partial trace everything was clear, and we get rho A was alpha square plus beta square, and then we had on the other diagonal term gamma square plus delta square, and on the off diagonal term we get alpha gamma star plus beta delta star, and the complex conjugate here, alpha star gamma plus beta star delta. So this is the reduced density matrix. Then the question was, let's try to find those states such that rho A is proportional to the identity. So it's 1/2 the identity of A. Okay? So which means that we have to solve this set of equation, that is alpha square plus beta square is equal to 1/2, gamma square plus delta square is equal to 1/2, and then we have alpha gamma star plus beta delta star equals 0, and the other thing, alpha star equals 0. Okay? And as you correctly pointed out, this is not, I mean, there are several solutions to that. Okay? So let's see. So let's try. So I would like first, as I said yesterday, to consider the case in which, so I would like to find solution in the case in which all coefficients alpha, beta, gamma, delta are real. Okay? So let's assume this. So you can check that there are actually several cases, actually 4 cases that solve this. So for instance, if you take alpha 0 and gamma 0, sorry, and beta 0. No, just a moment. I did some. Sorry, alpha 0 and delta 0. Okay. Then you see that if you take alpha 0 and delta 0, then this is solved. And then you have to take beta and delta equal to 1 over square root of 2. And so this is the state psi, which is equal to 1 over square root of 2 of, we said, alpha 0, which is up, down, plus minus down, up. Then there are other possibilities in which instead of taking alpha and delta, you take gamma and beta equals 0. So these two are equal 0. Then automatically these are 0 and this you take equal to 1 over square root of 2. And then you get those states.
I think up down we also have plus or minus in the first root, the first solution.
It's up down. Well, where is it?
I mean, alpha also can be plus and minus.
Yeah, I'm ignoring that.
Plus minus.
So you say here?
No.
I don't
If you
know.
put like that, so put it inside.
Do you want to have it here?
Yeah.
Ah, okay. This is true, but we know that two states which differ from a global phase are indistinguishable, are the same state. Okay? So what I want to say is the following. Suppose that you have alpha up plus beta down. Okay? So if you have the state e to the I phi, alpha up plus beta down, this, I mean, global phases have no effect, can never be detected. Okay? So states are defined up to a global phase. Do you agree?
Yes.
Now, if you agree, then you see that if you put here, so you can have plus minus, but you can also have minus plus. Okay? But out of this four combination is the same as having just putting plus minus here, okay? But plus minus here means that you have e to the I phi, where phi is either 0 or pi, which is a global phase, so has no effect.
Yes.
Okay?
Yes.
Okay. So I will ignore this. Okay? So these are four states. The four states, these states are orthogonal. Okay? You can verify it. And form a basis on this, on the Hilbert space of the two spins. Yesterday I told you that these states have a special name. They are called Bell states. Now there are another possibility to satisfy this relation. Okay, so you can take the off-diagonal components. You just get alpha equals 0, beta equals 0, but then you cannot get the identity from the diagonal. Okay? Now, are these all the solutions? No. We did not discuss this yesterday. You see, if rho A is the identity, this means that if you take a generic rotation of the spin A, okay, the reduced density matrix will not be modified, because since it's proportional to the identity, if you just do a rotation on the spin A, it will not change rho A. Is this clear? You should say yes or no, or you should say something, because otherwise.
Yes. Is it because rho is equal to rho plus?
Sorry? No, rho A is the identity, okay? So if you do a rotation of the spin, identity will not be modified, right?
Yes.
What about the others?
Yes.
Okay. So I don't know. Let me see. Chapter is not okay. Okay. So if you take all the states in which you do a rotation on the block sphere, they will have the same property. Let me make one example, okay? Suppose, do you see here? Do you see here? This is already is still okay, right?
Yes.
Okay. So, let's say this is X and this is Z. So this, do you remember there was a north pole and a south pole? So this is up and this is down, okay? So you can do a rotation going from the Z to the X, and you can take these other bases. Up plus down, and up minus down. Okay? These two states are still orthogonal. They are just obtained by doing a rotation along the y-axis. Are you with me or not?
Yes. We are thinking. I think sometimes we need some seconds to think and then to respond.
Yes, that's fine. Now respond. Is it okay or not?
You say that when you rotate the spin up along the y direction, along y, and then we got another state that orthogonal to the initial state.
Yes.
Yeah.
Okay. Good. So for instance, if you take, instead of if you apply a rotation here to the spin A, basically you get another family of states which obey these relations. Let me write it explicitly. If I take psi, let's say psi tilde equal to 1/2, and you have up plus down times down plus minus up minus down times up. If you take this state, this one, which has been obtained by simply rotating the first spin, and you do the partial trace, you will again obtain rho A proportional to the identity. So this means that starting from these four states and just doing all possible rotation in this three-dimensional space along x, y, and z, okay, then you can generate all the states that have the property that the reduced density matrix is the proportional to the identity. Okay?
Sorry?
Yeah.
Can you re-explain the expression of psi theta?
Yeah. So, by assuming that alpha, beta, gamma, delta are real, then I found these four states satisfying the requirement I posed. Okay?
Yes.
Now, I would like to convince you that these are not the only states. Let's see, I'll try to do it differently, okay? So can I erase the density matrix? This one?
Yes.
Yes.
No. So, rho A is equal to 1/2 the identity, okay? Which I can write as also 1/2 up plus down, okay? Now, this is rho A. So, suppose that I want to do a rotation, so it's a unitary operator, okay? That apply to the state psi, I will get some other psi prime. Okay?
Yes.
Now, this is clear. Now you see that if rho A, sorry, let me write it more. If I do the same thing on the density matrix, then I have to do U, and here I have U dagger, okay? And this I will get psi prime, psi prime. Okay?
Yes.
Very good. Now, so I erase this because I need some space. Now, if the state of the reduced states of the spin A is the identity, means that if I apply rho A and then I do a rotation U and U dagger, this is just equal to rho A because it's the identity. Okay? So, if I found, so let me call it this B1, 2, bell 1, 2, and B3, 4, okay? Just to keep it in mind. If I found psi B1, psi B1, for example, if I apply a rotation, okay, on the spin A, then you see the reduced density matrix is still rho A. This means that if I apply a rotation to this state, I will generate another state with the same property. Do you agree?
Yes.
So, if you do any rotation in the three-dimensional space x, y, and z, and you apply to these four states, you will generate all possible other states that have the property that the reduced density matrix is the identity. This is just one example in which the rotation just takes up in up plus down and down in up minus down. Okay? Hello?
Yes.
Is it okay or not?
Yeah, this is
The others?
Yes.
Okay. So, was there any other self-exercise? I don't remember. Or this was it?
We have another exercise,
Which was?
which is you give us two density matrix, and then you ask for the condition so that
Yes, I remember.
yeah,
Did you solve it or not?
yes,
And the result was?
they are orthogonal.
When?
And when two unit vector are orthogonal.
No, I think, so let me do it. So let me check it, okay? So I write it and you tell me if this is what you found, okay?
Yes.
So the two density matrix are, let's say, rho 1, 1/2, the identity plus n dot sigma, and rho 2 is equal, what?
N1 for one and
N1? Okay, let's call it N1. And 1/2 identity plus N2 dot sigma. Okay? Now, the condition I told you is the trace of rho 1, rho 2 should be equal to 0, which means that the trace, so I get 1/4 identity plus N1 dot sigma times identity plus N2 dot sigma. This is equal to 1/4. Then I have the identity, okay, which is 2, right?
yes.
I'm just doing the trace. Then I have the terms which is this times the identity, and the cross product is 0 because the Pauli matrices are traceless. Okay? So then I have a plus N1 dot, so the trace, I have to do the trace of N1 dot sigma times N2 dot sigma. Okay? So this means that I have to do the trace, sorry, I just rewrite it. So I have sum over alpha and beta of n alpha and beta trace over sigma alpha sigma beta. Right?
Yes, yes.
So you see that this is either 0 when alpha is different from beta, or is equal to 2 when alpha is equal to beta. Because the square of Pauli matrices are the identity. Okay? So this is equal to 1/2, and then I get 1 plus, so the sum over alpha means that I have n1 scalar product with n2. Okay?
Professor,
Yeah.
can you repeat the explanation you have given on the square of the Pauli matrices?
So the square of the Pauli matrix is the identity. You have to do it. Just try it. So for instance, if you have 1 minus 1, 0, 0, which is sigma z, is 1 minus 1, 0, 0, this is equal to 1, 1, 0, 0. Okay? And this is true for all them. So you see that in order to have this condition here, then you want that n1 dot n2 is equal to minus 1.
Actually, I don't understand why you have from the first line you go to the second line. I mean, from the trace of
Yeah.
and you go to the equal
Go to
to 2
here.
plus.
Okay. So I have to multiply this, okay? So I have identity times the identity. Then I have n1 dot sigma times n2 dot sigma, and then I have the cross product. Identity times n2 and n1 times the identity. Do you agree? No.
I'm still thinking because I recall.
No, don't worry. Just tell me if you
It's
agree.
multiplication, not the normal multiplication.
No, it's a matrix multiplication. No, but it's a matrix multiplication, right? But it's a. So, shall we do it? I mean, let me do it. Okay. So, I have the identity plus n1 dot sigma times identity plus n2 dot sigma. Okay? This is equal to the identity times the identity. Okay? So it's not a, I don't know how to write. So this is 1, 1 times 1, 1. Okay? Then I have plus n1 dot sigma times the identity. Okay? So which means that I have to do sigma x. It's 0, 1, 1, 0 times 1, 1, 0, 0. Okay? Is it okay?
Yes.
But I don't know if it's okay for the person who said it was not clear before. Cool. Can you speak up again, please?
Yes, I agree.
Okay, good. So you see that now the cross product, this one, you can verify that the trace is 0 because the Pauli matrices are traceless.
Yes.
Okay? So that's why the only term which remains are either identity or this times this, which is what they wrote.
Yes.
Is it okay now or?
Yes.
No, I mean, if you are not convinced, don't worry, you can say it. Don't worry, I can repeat it, I can do it as, don't say yes because if you are not convinced, because your voice does not sound too convinced.
So you can move on, and then I just need some second to process it, to organize it.
Okay, so let me do it, I do it step by step, okay? I just do it with the matrices, okay? So,
If you do all calculations, you will find.
so just a moment, let me do it in a single way, okay? I take just nx, so n1 sigma x, and n2 times sigma x, okay? So I have only 4 terms. So, and you see it immediately. This is 1/2 the trace of what? Of 1100 times 1100. Then I get plus n1 0110 times identity 1100 plus n2 the same 11 times the sigma plus I get n1 n2 and then I get 0 1 1 0. Sorry, I'm just, do you still see it or not?
Yes, I can see.
0 1 1 0, okay? Then you have to take the trace. So if you multiply these two matrices, the identity. So the trace is 2. This is the identity multiplied by this, and the trace is 0. So this will not contribute. The same here. However, if you multiply sigma x times sigma x, you will see that this becomes 1100. Okay?
Yes.
So it's the identity, so you get that the trace in this particular case is 1 plus n1 and 2. Okay?
Yes.
So the trace of 1 or 2 becomes 0 when the scalar product of n1 and 2 is equal to minus 1. Now, so this is for the exercises. Now we go back to perturbation theory. Just a moment, I have to just do something to clean the blackboard. So I will come in a second, okay? Just wait.
What are you doing?
Now, you got the same result as professor?
Yes. Yes.
Oh,
I
maybe.
did all the calculations.
Yeah, Yeah, and so the calculation, maybe I don't know what makes some point.
Yes.
Yes, sir. Yes, sir.
Messenger? Oh, okay. Great.
Okay, I'm back. So let's continue with the perturbation theory, okay? So just a moment. Now, what I want to do is introduce a new paragraph to perturbation theory, and then, which is very simple, and then I will go back to what we did in the previous lectures and do some examples. So this example, in part, I will solve it here. In part, you have to do it at home, and then we can check, say, either on Thursday or next week. Now,
I'm sorry.
yes,
I have a question.
yes,
About my last lecture. Your A plus A double cube
Yes.
equal to A cube plus A double cube plus B n A double plus B times n plus 1 times n.
yeah.
Can you, because the last term I didn't get it. Can you explain
Yes. So the question is, I have A plus A dagger, right? Cube, and this is equal to A plus A dagger, and then you have A square plus A dagger square plus A dagger plus A dagger A, right? And this is equal to, then when you multiply, it's A cube plus A dagger square plus A square A dagger plus A dagger A. So if I do some mistakes, just tell me, huh? Then you have A dagger A plus A dagger cube plus A dagger A cube, A dagger, and the last term is A dagger square A, okay?
the first term in the second line, what is it?
I'll just a moment, I have to double check. This one? one? No, sorry. The first term is just a cube. Sorry. Sorry, this is the first term is a dagger a squared. Sorry. Okay. Okay. Let's try to group them. So we have a cube plus a dagger cube. Okay. Then you have terms in which you have this one, and no, sorry, this one, and this one. Okay. So you have two daggers and one A. So you have plus a dagger cube square plus a dagger a dagger plus a dagger square a. Okay, plus you have the other terms. Okay, with two A's and where is the other one? Here. Okay, so you have a square a dagger, then you have plus what is it, the other, a dagger a, and then you have plus a dagger a dagger. Okay.
The last one is a dagger a square.
This one? No, I think it's okay.
The last term,
Sorry, yes, it's a square, yes.
Professor,
Yeah.
were you just rewriting the terms from the previous equation?
Yes, I just rewrite it because I want to show something. I just regroup it. I did nothing. So I just did the fact that there are. So you can see that these three terms are the Gaussian conjugate of these the three below, and the structure is such that you have something in which there is, you see here there is an imbalance of 1 between daggers and A. Do you see it? So here, these three terms, you have 2 daggers and 1 A. And while these other terms is the opposite. You have 2 A and 1 A dagger.
yes.
Okay? So the only thing you have to do is the following. So just take this term here, this one, a dagger, a dagger. Okay? This is just, so a dagger, a dagger is nothing else than n a dagger. Okay?
Yes.
Now, so for instance, this one, so then you have to play. So the only thing you have to do is the following. You have to do it many times. So when you have, so for instance, take this term here. You have a dagger A, okay? then you see that you have this AA dagger, but then you know the commutation relation between A and A dagger. So you know that the commutator of A dagger is equal to 1. Okay?
Yes.
So you know that A dagger minus A dagger A is equal to 1, which means that A dagger is equal to 1 plus N. Okay? Now, basically you have to use all this commutator in such a thing that you have to bring. So, this is what you have to do. Is this clear or not? So the only thing you have to just rearrange the operators in such a form that you will bring it something like N, A with some coefficient in front. Okay? And you have so, in this term here is immediate because it's just N A dagger. Okay? In the other terms, this is something you have to do. For instance, let's take this one, okay? So you have A dagger, okay? But then A dagger, so I'm making a mess, so let me write better. So take this term here. So you have A, you have A dagger square, but this is equal to A dagger. This is equal to what? 1 plus N A dagger. Okay? So yeah, A dagger plus N A dagger. Then you have to play with all this sum. So some of this term will simplify, and then you should get the expression I wrote. Okay?
Yes.
So there was a question, sorry, in the chat. No. Okay. So the first case we study for the theory, for the perturbation theory, was the case in which the spectrum of the quantum system we are considering is non-degenerate. Okay? Now, oh, by the way, sorry, did you solve the problem with x4, with the harmonic, with x4 to the power 4? Did you do the exercise? Or not yet?
Not yet.
Okay. Now, in the case of non-degenerate perturbation theory, I hope I managed to explain the fact that individual states and level, they have their own individuality that persists also in the perturbed system. So schematically, if I plot here the perturbation, say lambda, this is 0. So I have two levels that in the unperturbed case are here and there. So I may have 3 levels, whatever, okay? So E3, E2, and E1. So in the presence of perturbation, this will be modified, okay? But there is still a clear identification of what was the unperturbed level. So perturbation theory does not allow to describe two levels which are crossing or they are changing position. So something like this, I mean, it's not possible. Perturbation here, theory breaks down. So this is not something you can describe with perturbation theory. And the way to see to quantify how small the perturbation should be such that perturbation theory is valid is just to consider how the perturbation modifies the level spacing. So this is something we saw for the X cube. We just saw that level spacing, so the spacing between two levels, two neighboring levels, if you compare in the absence and with perturbation, you see that at some point things break down and perturbation theory is not valid. Now, why this implies that we cannot use the formulas that we derive for the degenerate system. So just imagine that you have a degenerate system, so phi 0 of n, so the nth level has some extra index which labels the degeneracy. Okay? So this state, this set of states will have an energy E0n. So you have this, in general you have to solve this problem. Phi 0 equal to E0 phi 0. Okay? So, but then at some, I mean, it can be all the spectrum or part of it, it does not matter. So you have that corresponding to a level n, okay? You have an index alpha which gives the degeneracy. So, can you give me one example in which, so for instance, if you take hydrogen atom, okay? So the ground state is non-degenerate, so the 1s. If you go to the n equal 2, okay, you have quantum numbers L and M, okay, which however do not affect, unless you consider other terms, spin-orbit, other things that I will not discuss. But if you solve the hydrogen, the simple hydrogen atom case in the absence of external fields and things like that, then you find out that the energy depends only on which quantum number. Question?
What is the question again?
So in the hydrogen atom, the states are characterized by which quantum numbers?
S.
No, so the principal quantum number n, and then
and
L and
L, M,
and
MS, NS.
n. Yeah, right. So L corresponds to what? To the eigenvalue, to the angular momentum, and M
spin.
no, to the projection of the angular momentum on the z-axis.
Yes.
Okay? So you have the principal quantum number n, then you have since you have a symmetry which is spherically symmetric, then you have also L and M as a good quantum numbers. Okay? So if you take the level 1s, is it degenerate or not?
No.
No. If you take the level the n equal 2, is degenerate or not?
yes.
Yes. Okay, because you have different values of L, M that may correspond to n equal 2. Okay, so in that case you have in some part of the spectrum you have some degeneracy or non-degeneracy, in some other part of the spectrum the degeneracy changes. Now, suppose that we would like to apply the formulas that we gave before, so before a few days ago, to the case in which we have perturbation. Now, you remember that in the second order perturbation theory, there were these denominators, which were energy differences, taking two different states. And it was crucial that all these energy differences, like E0m minus E0m, were different from 0. Now, if you have a degenerate spectrum, then you may have the case in which to two different quantum numbers, they will correspond the same energy. And therefore, this denominator, the fraction will explode. Physically, so what is the physical reason for that? If you have a degeneracy, so how can you define, or how can you introduce a concept of smallness of perturbation? Because the splitting is 0, okay? So, whatever you do to the system, it's always larger than the unperturbed state where the splitting was 0, right? So, this corresponds to, let's say, this facts correspond also to the situation that if you try to apply non-degenerate perturbation theory to the case in which there are certain degeneracies, then the formulas do not work. So we have to do something else. Okay? So I'm going to show you what you are supposed to do when you encounter degeneracies in the spectrum. So, but before doing that, let me stress an important fact, okay? So you have an unperturbed system, H0, and suppose that you know the spectrum, so you know the eigenstates and the eigenvalues. Now, as in the previous case, we want to study the eigenvalues and eigenstate of the perturbed system. Okay? Now, if you apply a perturbation lambda, the perturbation lambda can, in principle, remove all or parts of the degeneracy. Is this concept clear, or you know already, or should I discuss? Because this is important.
Yes, Professor, can you repeat the statement? I know for sure that the degenerate perturbation theory will remove degeneracy, but
Yes.
it could add.
So, perturbation in general will remove the degeneracy. But however, this is not always the case, in the sense that the degeneracies can be also removed partially.
Oh, I see.
So it's not that if you have an n-fold degenerate subspace, then you apply a generic perturbation and this will remove all the degeneracy. Okay? The system will become, some of them will be removed and some of them will remain. Okay? So this is important to keep in mind. So, let's so you know that, so do you know, so
Professor,
yeah.
interruption. But can you give us some hint about why it says remove partially?
Yes, I was about to say this. Now, degeneracies in the spectrum in general correspond to symmetry of the system. Okay? Is this known to you or not?
Yes.
Very good. So when you apply a perturbation, then in general you may remove all the symmetries which were present in the initial Hamiltonian in H0, or you just remove part of the symmetries.
Yes.
And if you remove part of the symmetries, it may as well be that the spectrum will become non-degenerate, but still some degeneracies will remain. Okay? Let me give you one simple example, very stupid. Okay? Just imagine the following. It's just suppose that you have a spin 1 system. Okay? Spin 1. So Sz is equal to 1, 0, minus 1. Okay? Spin 1. Now suppose that you have it is not important to find the origin of this term, but in principle you may have terms like this. B, Z, or B, let's say BZ, SZ squared. Okay? So it's quadratic coupling. It's not really linear Zeeman, but you have also you have such a term. it does not really important to discuss when this may occur, just keep it in mind. Now, if you have a system in the with spin 1 in the absence of magnetic fields, then all the spin component will be degenerate, right? So, okay? So because there is nothing in the Hamiltonian which depends on the spin.
Yes.
Okay? Now, if you apply such a term, then you see that the terms with the up spin and minus spin will have an energy will differ from spin 0. However, since you have a quadratic term, they 1 and minus 1 will be degenerate. So this is one simple example in which you went from a threefold degenerate spectrum to the case in which you have one non-degenerate and one twofold degenerate level. Okay?
Yes.
If you had another term which was something which was linear, I don't put coefficients here, okay? SZ, then this will remove all the degeneracies because up, 0 and minus will have different energy. Okay?
Yes.
Now, so let's see what should we do when we have a degenerate spectrum. So I will start from this. So I have this set of states. They form orthogonal bases in the subspace, and they have all energy E0n. Now, if you just take a linear combination of those states, they are still eigenstate of H0 with energy E0, right? So if instead of taking phi 0, I just take phi 0 n alpha prime, which is something obtained by some rotation in the subspace. This is still an eigenstate of H0 with energy E0n. Okay? And up to now, I have a complete freedom to choose which basis I want to take. Now, it turns out that if I want to do perturbation in this degenerate subsectors as manifold, then there is one single basis which is the optimal choice. Let's see how we can find this. So I will proceed as before, and so I will just assume that E n is equal to E0 n alpha plus lambda E0 n E1 n of alpha. So you see that at zero order term, the energy does not depend on alpha, but the correction may depend on alpha. So I'm just assuming that they may depend. It may turn out that this is not the case. And in the same way, I just say, look, I just take phi 0 of n alpha, phi of n alpha is equal to phi 0 of n alpha plus lambda phi 1 of n alpha plus correction. Okay? Now, I will do the same as before. Okay? So just keeping in mind what I said before. So it will then turn out that what I'm going to do is to find a special basis that allow me to compute this first order correction. So as before, so I will just substitute this expansion in the Schrödinger equation, in the eigenvalue equation, and if I stop to the first order, what I will get is H0 minus E0 of n times phi 1 n alpha. Let's say I call it alpha prime, but it doesn't really matter. V minus E0 n alpha prime phi 0 of n alpha prime. This should be equal 0. Okay? So this is the condition in just equating. So the zero order term will be satisfied automatically because phi 0 are solution of this eigenvalue equation. Just equating the two right and left hand side, I will get this condition. Okay, which is very similar. Yeah.
Professor.
Yes.
Actually, I have a question. You said that we need to rotate the basis, right, for the case of degenerate perturbation theory.
I will go with that. I do not yet. Yeah. Go ahead.
I mean, I heard you mention something about rotation in subspace. So.
Yes.
Yeah. How and why we exactly do that?
This is something I'm going to say in 2 seconds, okay?
Okay.
So, up to now, the only thing you have to keep in mind is the following. If phi 0 is the basis in the degenerate subspace, and if you do a rotation, also the rotated basis is form a set of eigenstate in the degenerate subspace. Okay? Is it okay this point?
Sorry. Can you repeat?
Yeah.
Yeah.
So up to now, the only thing you have to keep in mind is that in a degenerate subspace, this set of states is not unique, because if you can do a rotation here on this basis, you get another basis, and this will still satisfy the eigenvalue equation with the right eigen energy. So when you have a degenerate subspace, there is no unique way to choose the basis of the eigenstates, because any rotation within the subspace will give you a new set of eigenstates. Okay?
Yes.
Okay. This is the thing.
Sorry, Professor. I want to ask this. Could be a stupid question, but just to.
Don't worry.
So if we look at our set of basis functions, say we look at psi 0 and alpha, the one written at the left side. Yeah. Okay. So we have just to understand the levelings carefully. We have n, which tells us the levels of the degeneracy.
Yes.
And we have alpha, which tells us.
No, sorry. So n. So suppose the following. So imagine that you have n equal 1, n equal 2, n equal 3.
Yes.
Just for the sake of, and then I take n equal 2, we'll have 3 degeneracy. So here alpha is equal to 1, alpha is equal to 2, alpha is equal to 3. Okay?
Yes.
So n is just gives me the position of the level, and alpha is the index, which goes up to the. So I have to sum up here alpha prime from 1 to g, where g is the degeneracy of the level. Okay?
Yes. And then the 1 is just the perturbed states.
Where?
If we write psi of, for example, in the basis.
Yes.
Yes.
So what I'm looking for a correction to the unperturbed eigenstate.
Yes.
And this is the phi 1. So 1 is just the order of perturbation.
Okay.
Okay?
Just
now, an important thing that you have to notice is that E0 n does not depend on alpha.
Yes.
Because the level is degenerate. The correction may depend on alpha, which shows that by including some perturbation, then the level can stop being degenerate. Okay?
Yeah. Okay. Thank you.
So if I assume, yes.
Professor, I have a question for the equation at the bottom.
This one.
You wrote V minus E0 and alpha prime. So you said E0 does not depend on alpha, but
But
what about that one?
Sorry?
What about that E0?
E0 is the unperturbed eigenvalue.
Oh no, I mean the E0 on the equation of.
Sorry, because I did it wrong. This is E1. This was a mistake, my mistake.
Okay.
So this is E1, thank you. Okay? Now, if I multiply, as we did it before, with phi 0 of alpha, everything. Then you see that this term vanishes, because this is n alpha, okay? Because you get E0 minus E0, so this vanishes. And you have remained with a condition, I just write it here, phi 0 n alpha v phi 0 of n alpha prime is equal to E1 n alpha delta alpha alpha prime. So, so this is the result. In order to find the first order correction to the degenerate spectrum, what you have to do is that you have to take the basis that diagonalize the perturbation. And here I'm connecting to this rotation of the basis. Out of all the possible choices of the basis for the degenerate subspace, then the optimal choice that will give you the first order correction is the one which diagonalizes the perturbation. Now, at this level, then you can proceed this way. If you find this one, then you find first you find the first order correction, and then you can use at this point, then the spectrum has become non-degenerate, and then you can start from there just to apply non-degenerate perturbation theory.
Professor.
Yeah.
Sorry, can you repeat the explanation of the equation again?
So,
thank you.
yes. So you see that I multiply phi 0 n here, and then this term is 0. You just see that it's 0, okay? Is 0, okay. So basically, the choice that I have to make in order to determine E1 is to look for a solution of this being 0 that I rewrote here. So you see, what is the meaning of this? I just have to take the matrix of the elements of the perturbation in the basis phi 0, and I diagonalize. Okay? Once I diagonalize, the eigenvalues give me the correction to E1. And the eigenstate, they give me the optimal, so the good basis that allow me to solve already the first order calculation for the degenerate perturbation theory. Once you do this at first order, then you already solved part of the problem. So suppose that all the spectrum becomes non-degenerate here, then you can proceed with the previous approach of non-degenerate perturbation theory. Okay?
Oh, okay.
I will give some more examples, so don't worry. So we can...
Professor.
Yeah.
Oh, what do you, sorry if this is quite stupid, and what do you usually mean by degenerate subspace? And I mean, when do you use subspace and not using subspace?
So first of all, okay.